Hello guys, this is Tanay Jain and welcome to my channel. In today's video, I'm going to discuss about the paper which I have written. Yes, I have written a paper on mathematics, one of the topics, number theory, Chinese Remainder Theorem. So the title is The New Corollary and a Method for Chinese Remainder Theorem. And in the preprint of this paper published on the Zenodo, which is a reputable website by CERN and the European Union, is in the description. So if any of you experts are there, like mathematicians or professors, seeing this video, I please request you to check my paper, check my preprint, and verify if my research paper is correct and in which journal should I publish it. So without ado, let's get started. So what is this about? So first, let me tell you about basic concepts of Chinese Remainder Theorem. So you know what is a remainder, a divisor, and a dividend, okay? And then a quotient. So if you take numbers like 17 divided by 3, 5s are 50. Okay, this is basics, full basics. So remainder is 2. Now let us take one more number, 20 divided by same number. Okay, sorry. Now you can see both of them are leaving the same remainder. For here we use a special type of symbol, or you can say operation, which is congruence modulo. So we can say that 17 is congruent to 20. Mod means divided by what? 3. So we can also say 2 and 17 are also congruent, because when you divide any number smaller than the number, for example 2 divided by 3, it will be the number itself. If you divide something which is smaller than the number itself will be the remainder. So here also 2 will be the remainder. Here also 2 will be the remainder. Here also 2 will be the remainder. So 2 is also congruent to 17 mod 3. So here I won't explain you the congruence modulo entirely. Here I am here to explain about my theory and my research paper. So now, for example, we have this one congruent. Okay, congruence. Okay. Now we have more congruence like this. For example, 3 mod. Let me just change the pen. 3 mod 17. 3 congruent. 17 mod 7. Mod. What should I write? Mod 5. No. Okay. Mod 7, yes, mod 7 is correct. And then any other we can write 2 congruent to 15 mod 13, like that. Okay, now we have 3 congruencies. Now how to solve these congruencies? Okay, for example, we don't know these values. For example, all of these values are same. Okay, now for example, we don't have the initial values. All of these values are same. Okay, and then this here, you can see this numbers here are nothing but co-prime numbers. Co-prime numbers, which are those numbers whose common factor is only 1 and 1 itself. So here the numbers are co-prime, and then here there is the same number. So to solve them, we have something known as Chinese Remainder Theorem. Okay. So Chinese Remainder Theorem has many methods to solve it. If you have seen YouTube or many textbooks, there are many methods to solve it. Okay, I'm not going in depth about the methods, how they have mentioned it, but I have found out 2 new methods and 1 new corollary. Okay, so first let us discuss about the corollary. So What is the corollary I have given? According to me, okay, if you take CRT in a form x congruent to n, okay, x congruent to n initial, x congruent to p initial, x congruent to m initial. Let us don't take O because O will be not that nice to mention here. I mean, it won't look good. Mod. Okay, now, okay, we have the same number here. Okay, so it is extension to the I think remainder theorem, CRT, but I think it is not that much mentioned in the textbook. I have never seen such corollary before. That's why I am proposing it. And then you add 1 here. If I'm not wrong, yes, add 1 here. Sorry, not 1, any arbitrary integer. Integer or natural number? I think natural number. Yes, natural number. So t, where t belongs to natural number. So here we can say that t is arbitrary and t belongs to n, natural numbers, okay? For this situation, okay, for this situation, for this format of the equations, I have proposed a formula to solve it. So x, let us call this xi. Xi in the sense the initial value, the smallest value of this, of x satisfying this equation, because there are infinitely many values of x here, okay? Remember that Chinese Remainder Theorem only solves for the smallest value of x here, not infinitely big, infinity number of values, okay? So here, to calculate xi, I have given a formula, is to find the LCM of numbers. All the numbers. Okay. LCM of all these numbers, ni plus t, pi plus t, mi plus t. Ni plus t, let me just do it, mi plus t and pi plus t. Okay, to find the LCM, okay, and just shift it here so it will be visible. Xi is equals to LCM. Oh, let us do something here. Let us make this n minus 1 and there n, because n minus t, sorry. This won't change the meaning of it, but it will make it easier to write it here. This is how I have mentioned in the paper also. Mod n I mod. So don't get confused here. It's the same thing which I have represented, but in a different way. Maybe the letters will be different in my paper, I guess, or maybe exchange with the top bottom, but you understand the meaning, right? Okay, now we did the LCM of ni, pi, mi. Yeah, because I don't want to write ni plus t, pi plus t, and mi plus t every time. So this, for simplification, I have done this. Okay, so this minus t. That's it. Yes, that's it. That's it. And then second value of and the equation to, so this is the value for smallest number which satisfies this value. We need a value, we need an equation which tells us about general solution. So what are all the values which satisfies this? I think this is already there in our textbooks, if I'm not wrong. And x generally is nothing but LCM of ni, mi, pi. It will be the number terms, the term you want, which term, first term, second term, multiplied by the original number. This is the simple equation. I think this is well known, so I'm not claiming this to be novel. But the corollary, I think it's novel. If the mathematicians, any of you guys think it's not, please tell me in the comment section and tell which paper already covered it. directly. Okay, indirectly, many papers have covered a lot of stuff about a lot of things. Okay, directly in the sense which I've used it directly. Okay, okay. So this is a formula for calculating for such types of equations, CRTs. Okay, that is why this is known as corollary, an extension to the theorem, so that instead of solving it in a big, in a long format and then finding this, just do this, and then you get the answer, and then you can find any solution of it. Okay, so this is my corollary. Now we have two methods to solve CRT. I think it makes it easier for someone to solve it. Okay, so let me just tell you about it. So the first method which I have discussed in my paper is the progressive. The name is actually big. I have kept the name big for some reason. Progressive okay. So before we move forward, okay, sorry for that. Okay, before we move forward with the two methods, let me give you an example. Okay, example of my corollary. Is it works or not? Does it work or not? Sorry. Okay, now let us take x. Let me just see what I've given in my paper. I just mentioned that same form example so that there will be uniformity. 3, 4, 6. Sorry, yeah. Mod for x for mod 5 and x 6 mod 7 x 6. And in many questions related to this come in exam also. I've seen many such types of questions coming in IOQ, RMOP, INMO, and then IMO. I don't think so such easy questions come, but I mean they can use this concept to ask questions, so it will be easier for students solving it, or maybe some experts. If you guys find it helpful, then yeah, it might help you too. So this is just an accidental discovery made by me when I was doing some preparations of my exam. Yeah, so right now let us try to solve this. Okay, now we need to find value of x here. Okay, according to my method, find the LCM of all this. 4, 5, 7. What is it? 140. LCM of 4, 5, x sign, right? 7, okay, into k. Okay, let us don't use that. Sorry, minus t. What is t here? 1. It can be any difference, okay? It can be 4 and 2, 5 and 3. It should be uniform across all three. That is why t is common here. Minus t. Okay. So what is LCM? So we know from here t is equals to 1. LCM is what? 140 minus 1, 139. So check now. You can use any, you can ask Google, or you can try to solve by yourself. Then what is the smallest number when divided by 4 gives the remainder 3, when divided by 5 gives the remainder 4, and when divided by 7 gives the remainder 6. Or let me ask for you. Okay, let me just ask it for you guys to confirm that this is the correct answer. What is the smallest number when divided by 4 gives the remainder 3, when divided by 5 gives the remainder 4, and when divided by 7 gives the remainder 6?
We're basically looking for a number that fits a few conditions all at once. Let's call this number x. So first, when x is divided by 4, it should leave a remainder of 3.
So you can see
Next, when x is
it's
divided by
actually
5,
solving
it
it.
should be
So I'll
the
show you the solution when it is
So
done.
x is converted to 4 modulo 5. And finally, when x is divided by 7, it should leave a remainder of 6, which means x is converted to 6 modulo 7. We can solve this step by step. One way is to start with the condition of moving 4 and 5 together, and then bringing the condition for 7. We look for a number that leaves a remainder of 3 divided by 4, and a remainder of 4 divided by 5. We can find the smallest number that meets those two conditions, then we'll adjust it to also meet the condition for 7. It turns out that if you do the arithmetic or use something like the Chinese Remainder Theorem, the smallest positive number that fits all three conditions is 59. So x equals 59 is the smallest number that when divided by 4 leaves a remainder of 3, when divided by 5 leaves a remainder of 4, and when divided by 7 leaves a remainder of 6.
So it is saying it's 59 it seems. So let's just test. Yeah, this thing is glitching out because it is not 59 because 65 divided by 7 leaves a remainder of 6, but 65 divided by 4 doesn't leave don't leave a remainder of 2, it leaves a remainder of 1. I mean, how? 59 is not the number. 59 is not the smallest number. When divided by 7, let me just check once. 3. When divided by 7, 59 leaves a remainder of 3. Okay, our ChatGPT is kind of wrong here. So let me just.
Good catch. Sometimes a little slip happens with these remainder puzzles. Let's rework it carefully. We want a number that, when divided by 4, leaves a remainder of 3. When divided by 5, leaves a remainder of 4. And when divided by 7, leaves a remainder of 6. If we do the math again, or just carefully go through the steps, the correct smallest number is actually 59. But if that doesn't work
ChatGPT.
when we recheck, it's possible I made a quick slip, so let me just confirm that again. We want a number that satisfies all those conditions. If we rework it, we'll find the actual smallest number is 39. So thanks for catching that. The correct smallest number that meets all three conditions is 39.
Yeah, so you can see ChatGPT is glitching right here. So let's ignore that and let's Google it once. That smallest. Okay, I'll just show you. I have to Google it. Because here ChatGPT is glitching, it's saying 35, 39 and 79, 59. So that makes no sense, so sorry for that. Yes, so let me ask Gemini. Yes, so as you can see here, okay, if you actually ask Gemini, it says, okay, sorry, the answer is 139. I hope you can see it. Okay, so ChatGPT had some glitches there, so it's kind of messed up. But here Gemini says 139, which is same as our result. How? Now if we take 139 divided by 7, what is the remainder? Okay, 6. How? 133, which is divisible by 7. I would say, how is the divisible by 7? 19 times 7 is 133. So this is satisfying. And then if you divide it by 5, it leaves a remainder of 4. Because 135 is divisible by 5. And lastly, when divided by 4. When divided by 4, it leaves a remainder of 3. How? 136. 136 is nothing but 44 times 3. So 44 times 4, sorry. So it leaves a remainder of 3 here, as you can see. So it is correct. Okay. So as you can see, our corollary is correct for this example and any other example satisfying this property. Okay, it would be correct. If you wish, check it out. Okay. Now let us move forward with our methods, two methods, progressive, optimized arithmetic method, I guess. Okay, I kept the name so big, okay, sorry for that. It's so big that even I forgot the name of the method. Progressive congruence satisfaction algorithm and optimized progressive congruence satisfaction algorithm, okay. So I kept this, or else I could have kept it some other name. Actually, I was planning to keep it as chop method. Because, in French Revolution, in our method we are using chopping the remainder and the mod, the divisor, not mod, dividend, the number in the left side of the congruent sign, and remainder. Okay, we are chopping them down since till we get our result. So I called it chop method and optimized chop method. But then I thought not to keep such names because such names would be, not formal or something. But that is why I kept the name as congruent satisfaction algorithm and optimized progressive satisfaction. So the optimized progressive congruent satisfaction algorithm. Yes, so let us go forward with our first method. Okay, first method actually states that it is full form is progressive congruent satisfaction algorithm. Okay, now let us take the same example. Okay, so that you can know the answer is correct. Okay, it's 199. So 3. Okay, forgot. Okay, I forgot. Let me just check the question again. Yeah, 3, 4. Okay, sorry for this. A number here, okay, not left side, right side. Okay, slip of a tongue. X 4, 6. This also works for which are not co-primes. Okay, I'll show you that also. Okay, I have mentioned that example in our paper. That it also works for numbers which are not co-primes. Now, what does my method say? Now, take this number. Okay, what's number? This number. Okay. Now, first take the LCM. Okay, then take this number. LCM, what is LCM? 140. But this would be, I think this example is so short because here if you just subtract this, okay, you have to subtract this and minus it. 129. Now, divide by this, and if it is satisfying yes or no, and then again go here satisfying yes or no. That is why it is known as algorithm, because we are checking each and every line. Okay, so this will be a short example. This is like exceptional case of it, so we won't use this. Okay, let us use one more example which I mentioned. X 5 mod 7. Okay, X 3 mod 6. So you can see that the difference is not same here, like the previous thing which satisfies the corollary, and then 6 mod 10. Okay. Now, okay, you guys try to solve this using a normal method. Get the answer. I'll show you in the Google also what is the answer. Now, first take the LCM. 7, 6, 42, 10, 2, 10. I'm not wrong. Oh, wait. Wait, how is this? CRT. I think it's not actual CRT. I made a mistake here. But, okay, let us take not for an so, here, let us just example here. 9. So, not 9. 8, 11. Okay. Let's put 11 here. Now, let us find LCM here. Now, 66 into 7. Mostly LCM is nothing but numbers multiplied, which is 462. Okay, 462 is the LCM. Now what you need to do is minus this. Okay, we get 2. 7 minus 5 is 2. Subtract 2 from here. Subtract 2 from 462. 462 minus 2. 460. Now here we get the answer as 460. Now the second step here. Okay, this is a question. Okay, let's separate it. Second step is subtract 7 here. Why? Because I have explained in my paper that if you keep on subtracting the number here, the answer won't change, the remainder won't change, because if you take 35 divided by 7 is 5. So the remainder is 0. minus 7. 28 is again 0 remainder. So it won't change if you divide the same number again and again. The remainder won't change. So 7. Okay, so if you minus 7 here, minus, we get 453. Now check the condition. Well, first check the condition for the 461. 460 is how much? 420, 426, 432, 438, 444, 450, 456. 4 is the remainder. So it is not satisfying. Let us try for 453. 453, 6, 42, 42, 333, 3. This is the remainder. So this is satisfying for this and this. Okay, if you can check for 7, it is still following. 440, 447. I know, 448. Yes, 448. 448. Divide by 7, 44, 6, 22. Yes. Okay. So this is satisfying. This is satisfying. This is satisfying. Is this satisfying? Now, let us check if this is satisfying or not. 11, where this is 1 remainder, 13, 2 remainder. This is not satisfying. Now we'll divide by the LCM of this both. Not 7, not 6, but the LCM of this one. So first, find this subtract it by with this difference of this. Then subtract it by this number. Then the LCM of this number. And then if you have a fourth one, LCM of all these three numbers. And so on and so on. Okay. So 453 minus 42. Okay. So 453 minus 42 is 114. Now check the condition is satisfying or not. 33, 8, 81, 4. Not satisfying. Again do it. So that is why it is algorithm. It is doing a feedback loop. Yes, no, yes, no. 9, 7, 6, 369. Okay. And 11, oh yes. Now check for it. 39, 6. There you go. Gotcha. 369. 369 is the smallest number. If you just check it once, okay? 7, when you divide by 7, you have 5 remainder. 362, which is 35, 1. Wait. 362. Oh, sorry. We added. Sorry. So 376. So 26. Wait. Yeah. Okay, so we add by 5. Sorry. We add 5 or subtract 5. So 64. Sorry. Here 14, yes, it is divisible. If we here subtract 363, which is divisible by 6. Not sure. But no. Oh wait, why am I subtracting? I have to add it. No. So if you add it, we get 372, which is divisible by 6. And if you add 11, we get 370. No, 38. Wait, what do we get? 380. Wait, why am I glitching here? 358. This is correct. 363 is not coming here. I think we made a mistake in this second step, I guess. So I made a mistake in the second step, I guess. Here. 33 is the remainder. 453 minus 42 minus 411. 411 minus 42 is 369. So you should subtract by 3. Oh, sorry, 363 name. 366. 366 is divisible by 6. Yes, so I have not made any errors. It is 369. So xi is 369, and the equation is 369 anything. Okay, k plus. Sorry. Why am I glitching now? 462k plus 369. Okay. So this is it. Now if you want to check, I'll check it for you. Okay. I'll check it for you. Okay. Just wait. Okay. Can you find the smallest number when divided by 7 leaves a remainder of 5, when divided by 6 leaves a remainder of 3, when divided by 11 leaves a... Wait, sorry, the microphone is not on. How stupid I am. Find a number that is the smallest and leaves a remainder of 5 when divided by 7, leaves a remainder of 3 when divided by 6, and leaves a remainder of 6 when divided by 11. Okay, let me just okay. So here we go. I've typed it in Perplexity. It's a nice software. Oh my goodness. What is it doing? Okay, this is using some method here, so let me just ask Gemini itself. Oh wow. Yes, so as you can see here, I hope you can see it. The number is, oh no, 369. So even this method is efficient for small numbers and also for computational algorithms, because computers mostly run on algorithms. And then we can use this algorithm to power them and then find this remainders. I mean, it can be used for many branches of physics, if I am not wrong. Now, we have one more method, okay, which is efficient. That's why I have named it optimized progressive congruence satisfaction algorithm, okay? Yes. So, now let us begin the optimized progressive congruence satisfaction algorithm. The second method, which is much better and efficient than the first method. Instead of subtracting from the LCM and so on, we should subtract from the remainder, okay? So, here we have this first same step, LCM, which is 462. Subtract this from minus 2. And then, first now find with 6, with 6, mod 6. How much do you get? 4. Okay, because 456 divide 6. Now, subtract 42 from 42, the LCM, from this 4, not 460, 4. We get minus 38, sorry. We get minus 38. Now, same incongruency, there's a rule. If you subtract from here, we subtract from here. Here we'll do it later, okay? So here we'll do later. So what if minus 38? Minus 38. Oh, sorry, we should not subtract the LCM right now. That happens in the third step. We should only subtract this here now. Minus 7 is minus 3. So mod 6 minus 3 mod 6 is 3 mod 6. If you know congruence modular rules, so then we subtract one time. So 7 is like 1 time only. We got this. Now 11. Okay. 453 mod, I think 2. So congruent to 2 mod 11. Okay. 453 is congruent to 2 mod 11. Because here it's 1 remainder, 2 mod 11. Now, if you subtracted 42 here, we get minus 40. So we get minus 40 mod 11, which is nothing but 4 mod 11. So this is not the answer. Let us keep on going. From here, okay, we omit this step. From here only we go. Minus 82 mod 11. Now what is minus 82 mod 11? 6 mod 11. I think we need it. Okay, so how many times? 1 time, 2 times. So minus 84. 42 times 2 is 84. So minus 84. So what do we get? 369. Same as before. This is the optimized progressive congruent satisfaction algorithm. And this is much efficient because here we only deal with remainders, not the dividends, not the LCM. So which is going to be easier. As we don't divide the bigger number, now we should only add multiples of either the LCM or the single number with the number, which gives us the answer. I hope you loved my video and then like my theory and the research paper. The PDF of the research paper and the link of the preprint, Zenodo preprint, will be in the description below. And then if you want any questions or queries, if you have any questions or queries, and if you want any explanations of anything you want, please comment down in the comment section, or else like, share, subscribe. Thank you. Bye bye.